Welcome back. In this unit, we will discuss the nature of quantitative investigations, what does it consist of, what are the uniquity parameters in quantitative investigations, and we'll introduce the concept of similitude. All physical quantities can be classified on two different parameters, whether they're independent or dependent. Independent quantities are those which are in the control of the experimenter. They are something that do not even depend upon the phenomena. The dependent quantities, on the other hand, are those which are the results of the phenomena. I'll elaborate with examples just now. The other way to classify physical quantities is to classify them as variables or parameters. Variables are those quantities that change from point to point or from instant to instant in a given experiment, in a given phenomena. While the parameters are those values which are fixed for a given experiment and do not change from point to point or from one instant to another. They are invariant for a given experiment. Based on this classification, we can have four types of physical quantities: independent variables, independent parameters, dependent variables, and dependent parameters. We'll give examples to elaborate what we mean by them and what is the significance. Consider that the problem we are interested in is in finding the pressure distribution on an airfoil when it moves in the air. Clearly, the independent parameters, the parameters on which the experimenter has control, are something like this: the geometry and the shape of the airfoil, angle of attack of the airfoil, the forward velocity of the airfoil. These are all independent parameters. They do not change from point to point. They are not variable in a given experiment, in a given situation, in a given problem. Material properties: the air density, the air in which the airfoil is moving, the viscosity of air, the ambient atmospheric pressure. These are all independent parameters. They do not depend upon the phenomena. They are not results, they are inputs. So parameters are inputs. We choose the atmospheric pressure that we are working with. Or if we do an experiment, we measure what the atmospheric pressure is, and this is an independent parameter that does not depend upon the phenomena. All these parameters uniquely define the problems. If we have defined each one of these parameters, we have uniquely defined the problem. The problem definition is complete. The situation of the problem has been completely identified. If we change any one of these parameters, the experiment has changed, whether it's a numerical experiment, an analytical experiment, or a physical experiment. It is for these reasons that these independent parameters are termed as uniquity parameters. They uniquely define a problem, or there's a unique set for a given problem. The values of these would define a problem completely. Now let's look at independent variables. We're interested in pressure distribution. So the location of the point along the surface is an independent variable, location xy of the point along the surface of the airfoil. If the flow is steady, then time also would be the independent variable. The location does not depend upon the phenomena. It does not have anything to do with the fluid that you're dealing with. So these are independent variables. They change within an experiment. Different points, different times. Now let's look at dependent variables. Clearly, the pressure and the velocity components u and v on the surface of the airfoil, they change from point to point on the airfoil. They change with time in unsteady flow. So these are dependent variables. And these produce detailed results. They give us at every point what is the pressure, every point what is the shear stress, every point what is the velocity component on the surface of the airfoil, or even anywhere in the flow field. Dependent variables, they are variables and they are dependent. They depend upon the nature of the fluid motion. They are the results of the fluid motion. And then let's talk about the last category, the dependent parameters. Parameters are unique values for a given experiment. The total lift, there is only one value for the experiment in a steady flow. So it is a dependent parameter. It depends upon the phenomena. It is a result. So dependent. Total lift, total drag, or total pitching moment. We can define similar other quantities. Lift by drag ratio. They're all dependent parameters. They are the results and they are parameters. One value for a given experiment. What is an engineering problem? How does an engineering problem look like? The engineering problems is to determine a dependent variable or a dependent parameter as a function of independent variables and the uniquity parameters. Dependent variables are functions of independent variables and the uniquity parameters. The uniquity parameters define the problem and independent variables are results at different points. Those are the independent variables. So dependent variable is a function of independent variables and uniquity parameters. Or if we are interested in a dependent parameter does not depend upon independent variables. A dependent parameter is function only of the uniquity parameters. Give you an example. So to determine pressure as a function x and y, the location of the point on the airfoil, we separate by a semicolon and then list the uniquity parameters. The shape of the airfoil, the velocity far away, alpha the angle of attack, the density rho, viscosity mu of the fluid, and P atmospheric, the atmospheric pressure. These are all independent parameters. Similarly, the velocity u could be a function of the same set of independent variables and independent uniquity parameters. Or if the result desired is a dependent parameter like lift, the lift force L is a function of the shape, V naught, alpha, etc. Function only of the uniquity parameters. The independent variables are not in this list. This is the nature of the engineering problem. We can solve it by writing the governing equations and the applicable boundary conditions and initial conditions and solve them analytically. This is the method of engineering problem solving that has been introduced to you in your high school and in early part of your engineering curricula. Or by writing a computer program. And when we write a program, we have to give in the specific value of the uniquity parameters. We have to define an experiment. We can't find the result in terms of V naught, the free stream velocity. We have to give in the velocity V naught, and the result will be a number. So that's why many scientists call a numerical calculation as a numerical experiment, because we are doing it for one set of uniquity parameters at a time. The third method is we can do physical experiments for specific values of the uniquity parameters and make actual measurement using appropriate sensors and instruments. Thus, we could make the aircraft. The wing flies with this airfoil, have ports on the wings, along the chord, along the surface of the wing, connect each of these holes, these ports, to a pressure measuring instrument and measure the pressure when you fly the aircraft at a given speed, in a given atmosphere, with a given density, with a given viscosity, and so on. Now, what is a similitude problem? That is, this course is all about. The whole business of similitude is to determine the conditions under which we can predict the values of dependent quantities, variables or parameters, for one set of independent parameters, that is the uniquity parameters. For one set of uniquity parameters from those obtained from an experiment, physical or computation, with different though related values of the independent parameters. That is, for example, we have to find the pressure distribution in the flow field of the flow past this prototype cylinder with a given velocity VOP, with a given pressure POP, and etc., etc. We do an experiment on a model. We don't work with this, but we work with a model of a different size, geometrically similar, with a different velocity, different pressure, could be different density, could be different viscosity. Can we predict the results for the prototype experiments from the result obtained from model? Of course we can, but only under very restrictive conditions. The uniquity parameters of this problem must be related to the uniquity parameters of this problem by a set of rules which are known as modeling rules. And then, if those modeling rules are satisfied, we can obtain the results of this problem from the results of this problem by using appropriate prediction rules, which are also developed in the theory of similitude. This, in brief, is the basic problem that we will deal, the core problem that we will deal in this course, to find the modeling rules and to find the prediction rules. Modeling rules so that the two problems are similar, and the prediction rule so that we can make the required prediction. Thank you.